All right, here's the fifth problem. If Saturn were compressed until it had the same density as Jupiter, what would the new radius be in kilometers? Compare it to to Jupiter's actual radius, which is about 69,911 kilometers. Jupiter's density is 1.33 grams per cubic centimeters. Saturn has a total mass of 5.682 times 10 to the 26 kilograms. All right, we need an equation to solve this one, and here let's look at the formula sheet. Well, here's the equation for density. Density rho is equal to mass divided by volume. So what in the formula sheet, I rearranged this and solved for the volume. I'm sorry, did I say? I think I said volume. If I, sometimes, sometimes it's confusing. So it's usually like lowercase v is anyhow. This should be density is mass divided by volume. All right, and the volume is, so rearrange that equation and solve for volume. It's mass divided by density. So we need that equation, and the volume will be in cubic centimeters. Just to let you know, of course, the volume of any sphere is 4 times pi divided by 3 times the radius to the third power. However, if you're solving for if you know the volume, which we're about to figure out, and it really wants us to solve for the radius. The radius is the cube root. So all I'm doing is, all I did here is solved this equation right here. This equation. Well, I don't know if I can. This equation, and for r, and so that's what this is, right? And so that's ultimately what we're going to use: the cube root of 3 times v, right? Because all I did is bring the 3 over and then divide by 4 pi. And of course, since r is cubed, we have to take the cube root. All right, so we'll keep that in mind for when we do this. But we're going to start off with this equation right here to figure out the mass. All right, so let's get to it. We're sorry, we're going to figure out the volume. All right, so let's go back to this. All right, so we have this. We know that the volume, all right, and that's right on the sheet, is the mass. In this case, it's the mass of Saturn divided by the density of Jupiter. All right, so this is going to be the mass of Saturn, right, which is given to us as 5.682 times 10 to the 26th. See, that's not even right? Because that's kilograms. All right, so here, let's change it right away. So that's kilograms, and then we know that there are, you know, there are 10 to the third grams in 1 kilogram. All right, so we actually have to change this to grams. All right, so and all that does is this 10 to the 26 times 10 to the third, it just becomes 10 to the 29th. So if I rewrote this, here, let me just do that. The volume becomes 5.682 times 10, see, 10 to the 26, you just add the exponents. 10 to the 26 times 10 to the third would be 10e29. And now 29, and now it's in grams. That's supposed to be a 9, sorry. And now I can divide it by the density of Jupiter, which is 1.33. Right, and I think I had that. Yeah, there it is right there. 1.33 grams. This is a 3, sorry. It doesn't really look like a 3. 1.33 grams per centimeter cubed. And then the grams cancel, and it's cubed. And then since this is 1 divided by centimeters cubed, the centimeters cubed comes up to the numerator, right? So here, let's figure out what this is. So it's just this number divided by 1.33. All right, let's see. Here's our calculator. There's our answer from the last one, which was 1.9 times 10 to the 27th. I think I showed you that. Most calculators would have just given you, I know I'm still talking about the last problem, but most calculators would have given you given you the answer in scientific notation. You wouldn't really have to play that little game. All right, so anyhow, 5.6, 5.682 times 10, where's my EE button, or EXP, to the 29th, right? 10 to the 29th. Let me just show you. Like, if I say times 10 to the 26th, and then multiply that time, no, see, it's going to, I don't know why it doesn't show you in scientific notation. Divided, it says times 1,000 is equal to, so you to just give you more, so it just becomes 5 points, that's what this number is, 5.682 times 10 to the 29th. All right, and then again, we just divide that by 1.33. All right, so divided by 1.33. All right, so that is our new volume. So it's going to be I mean you could literally count the see the decimal points right here. So let's see that there's 3, 6, 9, 12, 15, 18, 21, 24, 20, 27, 28, 29. All right. So it's 4 points. So the new volume would be, let's write it in better terms than that. Much easier to look at. 4 point, what was it? 7.2, 4.27, 4.27. Yeah, that's perfectly fine. 4.27. That's a decimal point times 10 to the 29th. All right, and remember that's going to be, because this cubic centimeters in the denominator, it comes up to the numerator centimeters cubed. All right, so that is the volume if Saturn were crushed down to a density, a much. Remember, Saturn's density is about 0.7, so you'd have to crush Saturn down. All right, so then now we can actually solve this for the radius, right? All right, so now. Yeah, let's just do that. All right. So recall, I told you that to do that, you just use this equation. The radius is going to equal the cube root of 3 times the volume divided by 4 pi. All right. So that's all we're going to do. So now I have the volume, right? This is, you can think of it. This is an approximation of the volume. And then in the calculator, that's the exact volume. All right, so I'm going to multiply that by 3. Right, so I'm going to do what's under the square root first. So I'm going to multiply that. So it's times 3, and then divided by 4 pi. Right, so divided by, I'm going to put the 4 pi in parentheses, right? Divided by parentheses 4 times pi. All right, so that's both of those, the 4 and the pi, are in the denominator. All right, so this is what's underneath the cube root. All right, and now I have to take the cube root of all that. And so the cube root will give us the answer in centimeters, right? Because if I'm in cubic centimeters, the answer will be in centimeters. All right, so now for this calculator, let's see, can I do this? Let me show you. All right, so a lot of calculators have a cube root button. This one doesn't. So what I'm going to do is, just to recall, the cube root is raising something to the 1/3 power. So I'm going to raise this. Now it's got to be exactly 1/3. Okay, so remember, a third is a repeating decimal. So when I do this, I'm going to raise it to, in parentheses, 1 divided by 3. Otherwise, it's an approximation. All right, and then close parentheses. So that'll be exactly one. See, that's exactly 1/3. At least that's the way the calculator thinks about it. Is that's 1/3. We're raising it to the cube. That's the cube root. All right, so there it is. That's the size of it in. So if I wrote that number down, that would be um, in centimeters. All right. Now I don't want it to be in centimeters. Notice up here it says blah blah blah. New radius in kilometers. Right. It says it right there in kilometers. All right. So you might recall when we did this before to go from centimeters. Sorry, from kilometers to centimeters, you use a factor of 10 to the fifth. All right, so all I have to do is divide this number by 10 to the 1 times 10 to the fifth. So divided by 1 times 10 to the fifth, and this will be the answer in kilometers, because there's 10 to the fifth centimeters in 1 kilometer. All right, so that's it. That's the answer. All right, and I think it says round to one place to past the decimal. So this would be 4672. Sorry, 46,721.9. All right, so that's the answer. All right, so all right, so that's the, because you got to put the answer in kilometers, as we usually do for the radius of a planet. All right, so let's stop there. All right, this is problem, I think it's problem 6. Hold on, where am I? Problem number, where's the one I just copied? There we go. No, problem number 6. I was right. All right, so sorry, I'm wasting time. All right, so it says at its closest, the closest approach is about 8.5 AU from Earth. If the rings of Saturn are this size, so 270,000 kilometers in diameter, what is their angular size as seen from Earth? Round the final answer to the nearest whole number. Sorry, you don't want that. That's the angular size in arc seconds. We're going to do this in one. This part right there should not have been in there. This rounding, anyhow. We're going to find the angular size in arc seconds. All right. So the equation that we're going to need to change the distance, and I did that already. All right. So you change the distance from AU. This is what 1 AU is, and you get this many kilometers. All right. And so the equation is alpha. Remember, this is going to be in degrees. Is going to be 180 over pi. Right, we just did one like this, times the size of the object divided by the distance to the object. And so this is what we're going to use for the distance. All right, hold on, let me pause this. All right, so I've written the equation. Alpha is equal to 180 over pi, the actual size of the object divided by the distance to the object. These are the numbers right here. I plugged it all into my calculator. And so alpha turns out to be an angle in degrees, right? Because you have this 180 degrees up here. And then to convert that to arc seconds, we have to multiply this number by, there's 60 arc seconds in a degree, but then it's actually 60 squared, 60 arc seconds in an arc minute. All right, so you multiply by 60 squared, and this will change it into arc seconds. So the answer comes out to be 43.7.